All right, so for our last piece of chapter 31, I wanted to talk more about RC circuits. That is, circuits with a resistor and a capacitor. So here, our circuits do not have a nice constant voltage, constant current behavior the way that our purely resistor circuits do. In RC circuits, as we saw, we see this, exponentially decaying behavior. So the one that we derived in class was for a discharging capacitor. So if the capacitor starts out charged and we connect a resistor to it, we get a current flowing, through the resistor, and that I should write what this is. Discharging capacitor. And when this happens, as I explained in the lecture before, I'm not going to go into the differential equations again. The charge on the capacitor decays exponentially, the current in the circuit decays exponentially, and the voltage across the resistor and the capacitor also decays exponentially. So the equations for those are the following. So Q equals Q naught times e to the minus t over tau. More on tau in a moment. The current decays exponentially with some initial current times this exponential again, and our voltage, and in particular the voltage across the capacitor, is equal to the initial voltage across the capacitor times e to the minus t over tau. In this case, hopefully you can see the voltage across the capacitor is equal to the voltage across the resistor, so this equation works for the resistor voltage also. All right, so this is what we get when we have a capacitor discharging. This tau here is our time constant, and it, for this circuit with one resistor and one capacitor, it is simply equal to R times C. If we had multiple capacitors or multiple resistors, we would want to find the equivalent resistance or capacitance and plug those values in there instead. And so, what is this amount of time? So we plug in an R, plug in a C, we get some number of seconds. So this is the amount of time it takes our circuit such that these values all decay by a factor of E. Right, so if I plug in t equals tau, I get e to the minus tau over tau in all of these, which is e to the minus 1, which is about 37%. So that is, the time it takes all of these values to decay to 37% of their initial values. All right. So for those of you who attended our activity on the last day of instruction in person, you have already seen this, but most of you in the class have not. So I also want to talk about charging a capacitor. Which is going to involve very, very similar ideas, but slightly different equations. So let's say we have something like this. We have a voltage source, and to keep things, for clarity purposes, I am going to use our epsilon EMF variable for the battery voltage. And then let's say we have this connected to a resistor, and in turn that is connected to a capacitor, and then the circuit is completed. So we have some voltage source, we have a resistor, we have a capacitor, and the capacitor is starting out with no charge on it. Okay, so we can write down some things that we know. So if we have a current, it is going to be flowing clockwise through the circuit, right? This is the positive side, this is the minus side. So we're going to have a current flowing like this. When that happens, this charge is going to be building up on the capacitor. So if I is positive, Q on the capacitor is increasing. So in other words, the change in that charge over time is just equal to the current. For our discharging capacitor equation, we had a minus sign here because the current was coming off of the capacitor, but in this case, our current arrow, as we've defined it, is going onto the capacitor, so we do not have a minus sign there. Okay, so we know this. We also know from the loop law that, we can just do this really quickly, that our EMF, the battery voltage, minus IR, minus the capacitor voltage, which is, of course, the voltage over, the charge over the capacitance. So V for the capacitor, the charge for the capacitor is equal to C times delta V, so delta V is equal to Q over C. Okay, we'll just say that so I don't have to trip over my words here. So what the loop law tells us is that the EMF minus IR minus the capacitor voltage times C, minus just the capacitor voltage, voltage equals 0. So we can rewrite this as E equals IR plus delta VC. Okay, we know that this I is equal to dq dt, and we know that delta VC is equal to Q over C, and we know that this is equal to some constant. So this is another differential equation. It is slightly different than the other one. If we rearrange it to solve for dq dt, we get the following. dq dt is equal to, so I move this Q over C to the other side and then divide by R. So that is going to be minus Q over RC plus the EMF over R. So before, our equation looked kind of like this, I believe. Don't read my notes. Looked kind of like this. So we have this other term in here, and that changes the solution to this differential equation. And again, as I've said before, I don't expect you guys to solve this, or you don't even really have to understand the differential equation part of this. We're just going to use the solution. So I just wanted to show you where the solution comes from. So the solution to this in terms of the charge is the following, and I'm actually going to erase the other stuff so I can have a little more room for this. Okay, so our charge as a function of time is equal to some maximum value of the charge times 1 minus e to the minus t over tau, where this is the same tau as before. Tau still equals RC. And we're going to draw a graph of this in just a second. Before I do that, I also want to remind you that Q on the capacitor is directly proportional to the voltage. So the capacitor voltage as a function of time is equal to some max value times 1 minus e to the minus t over tau. Also, it is just this equation divided by the capacitance C on both sides. Okay, so this 1 minus e to the minus t over tau, the shape of this graph looks like this. So, for t equals 0, we get e to the 0, which equals 1. 1 minus 1 is 0, so we start at 0 as we want. At high values of t, this e to the minus big number goes to 0, so we're left with whatever this max value is. We're going to asymptotically approach that. So our graph is going to look something like this, approaching this max value. And this graph, this axis is time. This axis could be the charge or the capacitor voltage. Both of them are going to have a graph that looks like this because they both, those equations have the same form, just different by a multiplied constant. So our current, flows through the resistor, charge goes on the capacitor, and it starts off that charge is increasing rapidly, and the rate that it is increasing decreases and decreases and decreases until eventually it reaches this maximum value and the charge stops moving. All right, so we would like to know what the equation is for the current and the resistor voltage also, and it turns out, kind of like how these are the same form of those equations, the resistor voltage and the current also have similar form because of Ohm's law. That should not be terribly surprising. So that looks like this. So we can get these pretty easily. We can actually get by just taking the derivative of this equation if we really wanted. So that you can do that if you want to ensure that you get this equation. This initial current is going to be determined by the battery voltage and the resistance. So, right, we can also get between these two with Ohm's law, V equals IR. So if we take this equation and multiply by R, we get this equation. So I naught is equal to the battery voltage over our resistance. And that is because initially in the circuit, when we first connect this, our capacitor has no voltage difference across it, which means that it is, there is no delta V here, which looks kind of like that is just a wire, which means we have a battery, a resistor, and no delta V. So all of our battery voltage is across the resistor, which gives us a current of E over R. Yeah. All right, so anyway, these equations, you'll note, I didn't actually say this, these are exponentially decaying. So where these two are asymptotically approaching some, positive non-zero value, these I and VR are exponentially decaying, just like our equations for the discharging capacitor. So these two are the same equations for the charging capacitor or the discharging capacitor. These equations are different depending on if you're charging or discharging. And this value here is the the initial value of I or V. So that is either epsilon or E or E over R, depending on which variable we're talking about.